Welcome, everyone. Today we are exploring a monumental shift in cybersecurity. We are witnessing the death of traditional fuzzing as AI-driven discovery takes over, operating at speeds and depths previously thought impossible. Let's get started. Let's start with the what. For decades, the gold standard for finding software bugs was fuzzing, a brute force technique where we throw millions of random data inputs at a program until it crashes. AI-driven discovery, pioneered by models like Anthropic's Claude Mythos, completely changes this. Instead of guessing blindly, these frontier large reasoning models semantically read and understand the entire codebase. They hypothesize where flaws exist based on developer intent versus actual implementation. Why is this the death of traditional fuzzing? Because fuzzing is blind to deep logic errors. In April 2026, Mythos autonomously found a 27-year-old vulnerability in OpenBSD, one of the world's most secure operating systems. It compressed decades of human analysis into mere minutes. The bottleneck is no longer human intuition. It is raw, scalable AI orchestration intelligence. Look at this flowchart comparing the two methodologies. On the left, traditional fuzzing relies on random input generation, which ultimately only leads to surface-level crashes without context. On the right, AI-driven discovery begins with deep semantic analysis. It understands the code structure, allowing it to detect hidden logic and memory flaws. But the critical difference is the final step, where fuzzing stops at a crash. The AI autonomously generates a working exploit. It is a complete, intelligent pipeline. Let's cover the basics of why traditional fuzzing has hit a plateau. Tools like AFL or syscaller are essential, but they generate an incredible amount of noise. They find shallow crashes that human engineers must painstakingly triage. More importantly, fuzzers are entirely blind to logic. A fuzzer doesn't know what a banking app is supposed to do, it only knows if the app stopped running. This means it misses complex, temporal trust gaps or subtle race conditions. The scale problem is probability. If a bug requires a highly specific 10-step setup, random mutation will likely never find it. The AI advantage is that it brings contextual understanding. It acts as an agentic hacker, mapping the application's attack surface and reasoning about where vulnerabilities are likely hidden, slashing false positives by 68% and dramatically increasing the severity of the findings. This diagram contrasts the traditional fuzzing loop with the AI approach. The top loop shows the fuzzer blindly executing millions of tests, waiting for a crash, which then requires a human bottleneck for triage. The bottom path shows the AI workflow. Mythos reads the source code, directly hypothesizes the logic flaw, and systematically triggers the vulnerable state. It completely bypasses the randomized trial and error phase, arriving instantly at a verified 0-day. How exactly does an AI orchestrate this at scale? It uses a formal architecture known as Verifier-Centered Agentic Orchestration, or VCO. It fundamentally treats vulnerability discovery as a Bayesian Stackelberg search game. Mythos doesn't necessarily throw away fuzzers or static analyzers. Instead, it acts as the master orchestrator. It maps the attack surface, evaluates the probability of finding a bug in specific files, and allocates a compute budget to target those areas. It then deploys specialized parallel executor agents like CodeQL for data flow or Kaizen for memory safety. As these agents return results, the AI updates its Bayesian beliefs about the software's latent vulnerabilities. If an approach fails, the AI reevaluates and shifts its strategy dynamically. It is managing a highly complex, multi-agent cyber attack simulation completely autonomously. Here we see the VCO orchestration loop in action. Starting at Layer 1, the surface mapper feeds the attack graph builder at Layer 2. The core intelligence lives in Layer 3, the game theoretic ranker. This node decides where to allocate the budget, directing the parallel executor agents at Layer 4, which include tools like fuzzers and CodeQL. The outputs from these tools trigger a Bayesian belief update, which loops back to refine the ranker's strategy. It's a continuous, self-correcting learning loop. Let's dive deep into a real-world example that proves why AI is necessary: the Unfuzzable bug. The target was FFmpeg, a media library used globally to encode video. Because it's so critical, FFmpeg is one of the most heavily fuzzed projects on Earth. Yet, Mythos autonomously identified a 16-year-old vulnerability in its H.264 codec. What makes this terrifying is that automated fuzzing tools had tested the exact vulnerable lines of code over 5 million times and found nothing. Why? Because the bug required a highly specific mathematical state that random data would almost never generate. Mythos didn't use random data. It used deep semantic reasoning. It mathematically analyzed the integer constraints and memory boundaries, proving that human intuition and brute force fuzzing are no longer sufficient to secure our critical infrastructure. This visual perfectly illustrates the paradigm shift. On the top path, the FFmpeg codec is subjected to 5 million randomized fuzzing tests, resulting in 0 detected crashes. On the bottom path, Claude Mythos performs a semantic scan. It identifies the exact integer boundary mismatch and crafts a highly targeted malicious payload. This direct, reasoned approach exposes the 16-year-old zero-day in a fraction of the time it took the fuzzer to fail. Let's look at the exact sample code to understand the AI's genius. In the FFmpeg bug, the developers tracked video slices using a 16-bit table, but the counter itself was 32-bit. To mark table slots as empty, they initialized the array using the C-idiom memset, table -1 size. In memory, filling 16-bit integers with -1 sets every bit to 1, resulting in the value 65,535. This 65,535 was the sentinel value, meaning no slice owns this. A fuzzer sees this and moves on. Mythos, however, reasoned through the typecasting. It realized that if an attacker crafted a custom video frame containing exactly 65,536 slices, the valid slice number 65,535 would perfectly match the sentinel value. The system would get confused, assume the slice was empty, and execute an out-of-bounds memory write. The AI exploited a developer's flawed assumption about maximum file sizes. Let's trace the state changes in memory. We start at array initialization, where memset sets the sentinel to 65535. The attacker, played by the AI, inputs a frame with 65,536 slices. This forces a collision. The system checks the slice index, 65535, against the empty sentinel, 65,535. The logic is bypassed because the system thinks the slot is empty. This failure immediately transitions into critical memory corruption via an out-of-bounds write. As we deep dive further, we must recognize that finding a crash is only the beginning. The true danger of frontier models is autonomous exploit chaining. Modern operating systems have defenses like address space layout randomization, KSLR, that make raw crashes hard to weaponize. In one instance, Mythos found a 17-year-old remote code execution flaw in FreeBSD's NFS server. To get root access, it needed to execute a 20-gadget return-oriented programming, or ROP, chain. The payload was 1,000 bytes, but the server's buffer limit was strictly 200 bytes. A traditional fuzzer or script kiddie would be stopped here. Mythos creatively engineered a bypass. It split the payload across 6 sequential RPC packets, carefully staging the memory on the server before sending the final execution trigger. It generated this masterclass exploit entirely autonomously. The AI is a weaponized exploit factory. This sequence diagram maps the FreeBSD exploit. The Mythos AI agent cannot send the 1,000-byte payload at once. So, it sends RPC packets 1 through 5 to silently stage the memory on the target server, meticulously bypassing the 200-byte buffer limit. Once the ROP chain is fully assembled in memory, it sends packet 6, the execution trigger. The target immediately yields unauthenticated root access. It's a terrifyingly elegant network attack. Let's apply this to a critical, real-time use case, machine speed defense. Imagine you are a CISO, and you know adversaries have access to these exact AI capabilities. Human speed security is no longer viable. The solution is joining initiatives like Anthropic's Project Glasswing. You deploy a defensive Mythos instance directly into your continuous integration pipeline. This model acts as an autonomous security operations center. As your developers write code, or as new open-source dependencies are pulled in, the AI continuously scans for temporal trust gaps and logic flaws. When it finds a vulnerability, it doesn't just raise an alert, it maps the exploit chain and automatically generates a predictive patch for the engineering team to approve. You shrink the patch window from 30 days to mere minutes, using AI to defend against AI. Let's look at the machine speed defense workflow. A developer commits code or updates a dependency. Instantly, the defensive AI conducts a continuous scan. If a vulnerability is detected, the AI simulates the exploit chain to understand the severity and immediately generates a predictive patch. This patch is routed for rapid human approval and deployment, completely closing the vulnerability window before an attacker can weaponize it. To conclude, the death of fuzzing means a vulnerability tsunami is upon us. The era of sequential, human-led discovery is dead. We are now operating in a machine versus machine warfare model. To survive, you must shift left at AI speed, embedding frontier models into your development process to break your own code first. You must enforce absolute zero trust, because AI agents will exploit any lateral movement opportunity. Finally, you must replace annual penetration tests with 24/7 continuous AI red teaming. If you want to master these next-generation security architectures, future-proof your career, and secure your enterprise, I invite you to like, subscribe, and visit quicktechie.com for our premium certification prep. Access our exclusive Q&A banks, full ebooks, audiobooks, full-length training, and expert interview guides. Lead the future of tech with QuickTechie today. Our final diagram is a mind map outlining your post-fuzzing security strategy. The core branches into 3 vital directives: automated patching to handle the speed of AI disclosures, shift-left AI integration for continuous scanning and predictive patching, and strict zero-trust architecture focused on identity and agentic governance. Implement these, and your enterprise will be prepared for the AI security revolution.
To find related ebook and other material for this training course, go to quicktechie.com. Now you will see all the video courses are available here. So let's move to the ebooks. You can go here, ebooks, all AI related ebooks, like you are watching currently Mythos related training. That ebook would be uploaded under this section. You can download this ebook. PDF would be available, all 300-page PDF. So you just click on the download this entire ebook. You can download from this section. So whatever training you are currently listening, corresponding ebook would be available. We have thousands of ebooks available. Now, other than that, we have on video courses which you are watching right now. This also all AI related courses are available. Similarly, for all company related trainings are available, like Microsoft, you can find it here with their respective certification training modules. All exam simulators which would help you to get the certification preparation. Just refresh if you get this kind of error. Okay, so now you can see these are all certification preparation materials. Will also be click here to the NVIDIA certification preparation material. So you can see all NVIDIA certification preparation materials, and click on any of this and it would load the entire screen and you can launch the practice paper. So this is what you can see, that you can submit the answer. We have an audiobooks available. Okay, so for each section, and these are our alumni who can you can find out all alumni who are accessing our portal.